Hello everyone and welcome to MakeLearn 360. So in this video I want to solve a question or some couple of questions with you to illustrate the concept of axial loading and deformations. Alright, so let's begin. So with the first problem, we have a load which is we have a wire. Okay, so let me start 2.1. We have a wire which is having a length of 80 meters, okay, and then having a diameter of 5 millimeters. Now it's to be made of steel, so we have the length as 80, we have the diameter as 5 mm, and then the Young's modulus for steel is 200 gigapascal. Okay, now there is an ultimate tensile strength of 400 megapascal. So ultimate tensile strength of 400 megapascal. Okay, and then a factor of safety of 3.2 is desired. So we have the factor of safety F.S 3.2. Okay, now we should determine the largest allowable tension in the wire and then the corresponding elongation of the wire. Okay, so this question is sort of very simple and straightforward. All right, so the allowable strength, since we have the ultimate tensile strength, then the allowable tensile strength, so S allowable will be the ultimate divided by the factor of safety. So it's going to be 400 divided by 3.2. So meaning that whenever you have a factor of safety, then you can say that your allowable strength is your design strength divided by your factor of safety. So if I divide 400 by 3.2, I will get 125, and that is the one I will use in my calculation. All right, now since the allowable strength is this 125, then it means that that is the strength of the material that we are going to use. Okay, having known the strength of the material, then we can go forward and say that so we know that stress is epsilon and then multiplied by the Young's modulus. So this is equation 1. We also know that the stress is going to be the load divided by the area, and then this is 2. And finally, we know that the elongation, which is delta, is given by P L divided by AE, equation 3. So the first part of the problem, he said we should calculate the largest allowable tension in the wire. So the tension force will be sort of the load which will be in the wire. So to calculate this, we would have to use so the load is going to be the stress over the area. Okay, now it means that we have P as 125 megapascal multiplied by pi, and the diameter was what, 5 mm. So pi d squared, which is 5 squared over 4. All right, and what do you get from this? All right, so over here, if we pick our calculators, what do you get? So we are going to get 125 multiplied by pi. So pi multiplied by 5 squared over 4. Okay. So it's going to be 144.63. 144.63. Now, unit of this, I want to talk about this. The factor of safety in some way, somehow, can also be taught as your allowable strength, your ultimate divided by um, your allowable. So, in other words, this is the stress that you are trying to allow. Okay. And that is the reason why we use the allowable strength as the stress, because that is the stress that we want. Is that right? Okay. So that if we divide this ultimate by the allowable, we will get 3.2. That is to say how safe we are. Okay. So now the load or the allowable tension will now be 1.4463 newtons. Okay, because this one is in megapascal, which is the same as Newton per millimeter squared. Therefore, if you multiply it by millimeter squared, you are going to get newtons. Okay, so the unit of the load, in other words, the tension, is 144.63 newtons. All right. Then the question said we should calculate the corresponding elongation. Okay. So when we say the elongation, what we are trying to say is that this wire is going to extend, okay, due to the application of the load or the tension force. This wire is going to extend. So if this was the original length, there will be some other length here which is added, and this is what we are calling the new length. Okay, but then the actual elongation, so what we have here is what we are calling the elongation. All right, and this elongation due to the load is given by this formula here, which is the load, the length divided by A multiplied by E. So it's going to be 144.63 multiplied by the length, which is so the length is 80 meters. So we are going to convert it. So 80 meters into millimeters will be 80,000 millimeters. Therefore, the area, so the area is going to be pi multiplied by 5. Then we can even multiply the 4 here. And then the Young's modulus is 200 gigapascal. So let's convert the 200 gigapascal into megapascal. That will be 200 times 10 to the power 3, so that everything will be in millimeters, and then the final answer that we will get will be in millimeters. But you can also choose to go in meters. Okay, but the best way to deal with a problem like this is that, because you don't want to get large values, it's better to be in millimeters. So 144.63 multiplied by 80,000 multiplied by 4 divided by pi multiplied by 5 squared multiplied by 200 multiplied by 10 raised to the power 3. So that is 2.95. So the elongation is 2.95. Okay. So basically what this means is that if we apply this load, there will be 2.95 millimeters extension at the end. That is what it basically means. All right. So this problem has been solved. Now let's look at the next set. So with the next question, he's saying that a steel control rod of length, so the same preamble, but this time round, the length is what? 5.5. Okay. So the length is 5.5 meters, 5.5 feet. Okay, so the length is 5.5 feet. Now the question is saying that the length should not stretch more than 0.04. What does it mean? It means that this distance here, if we were to look at that, it means that this distance for that question should not extend, should not go beyond. Okay, so therefore if it shouldn't go beyond that value, then it means that that is the elongation that we desire. So delta is 0.04. I hope the concept is clear. So delta is 0.04 because it shouldn't go beyond. That is what it means. It shouldn't stretch or extend beyond that value. And then the load is 2 kip tensile load. Okay, so we have a tensile load, which is what? So the tensile load P is 2 kip, which is the same as 2000 pound force. Okay, so we are thinking about something here, which is let's say a rod, and then there is this sort of tensile load here, which is applied 2000 pound. Now we are saying that this length here is what we have as the 5.5 meters, and that the extension, so we are saying that this shouldn't extend. Okay, it shouldn't extend beyond 0.04 inch. Okay, so that's basically the takeaway from this problem. Now he's saying that if we know, so knowing that E, which is the Young's modulus, is 29 times 10 to the power 6 psi, we should determine the smallest diameter rod that should be made. Okay, so E, which is the Young's modulus, is 29 times 10 to the power 6 psi. Okay, so we should find the smallest diameter. What do you think? The diameter is inside the area, isn't it? So how can we get the area? Let's try and find a relationship between all of this. So we can say that the extension or the elongation is actually given by PL over AE. Okay, now if we have L, we have delta, we have P, we have E, then we can find A, right? And the area will give us the diameter. In fact, we can even go ahead and say that our area is pi d squared over 4 multiplied by E. Okay, so that we are going to get everything in terms of the diameter. So delta is going to be 4 PL divided by pi d squared E. Therefore D, which is the diameter, is going to be square root of 4 PL, then we divide it by pi and then E. All right, having done this, let's put the values inside. So we are going to get 4 multiplied by P, which is 2000, multiplied by 5.5 feet, divided by pi, multiplied by 29.9 times 10 to the power 6. All right, but we have to be careful because you know, psi is pound squared inch, but we are in feet, so we need to convert this length to inches, but 1 foot is actually 12 inches, so we need to multiply by 12. So multiplied by 12, and when we do this, we will be able to get the diameter. So let's So it's supposed to be 0.04, which is the delta, multiplied by pi, and then 29, 10 to the power 6. So then our diameter is going to be so we just have to multiply here by 0.04, which is 0.381 inches. So that is the diameter we should expect, the smallest diameter we should expect. All right. So the first part of the problem has been solved. Now let's look at the second part of the problem. He says that the corresponding normal stress caused by the load. So the normal stress caused by the load is the load divided by the cross-sectional area. So the normal stress is the load divided by the cross-sectional area, which is 2,000 pounds divided by the area. And we know the area already, so it's just going to be pi multiplied by pi multiplied by 0.381, which is the diameter. So the 4 will come here. And what do we get? So we will get 2,000 multiplied by 4 divided by pi and multiplied by 0.381 squared. If we do this, so we have this one. Okay. So the stress is going to be 175. So 17542. Okay. 17542 psi. All right. So the problem has been solved. Now let's move to the next part of the question. So the last set. Okay. Now he says that for this last set, he says that we have two gauge marks which are exactly which are placed exactly 10-inch apart. So this is talking about the fact that we have a strat testing machine, and then the gauges are placed, so something like this. So the gauges are placed 10 inches apart. So that is sort of the length, which is 10 inches. And then the question says that on 1/2 inch diameter aluminum rod. So the diameter, so the length is 10 inch, the diameter is 1/2 inch. All right. So then okay. Yeah. So E is what? 10.1 times 10 to the power 6 psi. So E is 10.1 times 10 to the power 6 psi. Okay. So we are saying that we have the gauge between, so the distance actually, which represent the length inside the strat testing machine or the tensile test machine, 10 inches. We have the length, and then the diameter is what they are saying is half inch. Okay, and we have the Young's modulus. Now, if you look at the question, he said that there is an ultimate tensile strength of 16 ksi. Okay, so the ultimate strength is 16 ksi. So SULT 16 ksi. And then the question is saying that if we know that the distance between the gauge marks is 10.009 after a load is applied. So what do you think? We started with 10. Okay, we started with a gauge length of 10. Now we are saying that after we applied after we applied the tensile load, so this is how it actually works. Let me clean this one. So when you go to the tensile test machine, this will be stretched. So you will place your member inside, and then there will be a load going up and one load going down of the same magnitude, and there will be that sort of stretch. Okay, now after the stretch, we are saying that there is a new length. So it's like this will experience some elongation. Okay, so this elongation resulted in the length now becoming 10 point what 0. Okay, let me go back and see. So it resulted in an elongation of 10.009 inch. So 10.009 inch. What does this tell us? It means that there has been an extension delta, which is the change in length minus the original length, which is 10.009 minus 10. So from this question, the elongation is actually you know 0. It's actually 0.009 inch. So this is the extension after we apply the load inside the machine. Now the question is saying that we should determine the stress in the rod, number one, and then also the factor of safety. Okay, so let's determine the stress in the rod. So to find the stress in the rod, what do we have? So we have, okay, let's put this one aside because this one will not come in the calculation, but we know L, right? Okay, let's calculate the area from the diameter. It's going to be pi d squared, which is 1/2, or let's say 0.5 squared over 4. So the area is going to be pi multiplied by, so pi multiplied by d squared 0.5 actually over 4. So what is this? 0.196 0.196 inch squared. So this is what we have. All right, so we have the area, we have the extension, we have the E, okay, which is the Young's modulus, and we have the length. What do you think? So if you remember, I gave you 3 equations from the beginning. So we have this equation, we have this equation, and then we also have this equation. All right, okay. Now what do you think will be the formula to use here? It's going to be so E is here, L is here, and we want the stress. Okay, so this is PL over AE. We know this, but we don't know the load. Okay, we can also say that this is equal to this, right? Okay, now stress is changing length. Sorry, the strain is actually the original quantity. Sorry, the elongation divided by the original quantity is the strain. So we can replace this by this. Okay, so the actual stress will be given by the Young's modulus, which is 10.1 times 10 to the power 6, and then we will multiply this by the elongation, which is 0.009. Then we divide this by the original length. In fact, this is actually the formula to use. So I didn't add this one. This is called the strain. All right. So we can say that the stress induced, so divided by the original length, which was 10, right? Okay. So the stress induced is going to be 10.1 times 10 to the power 6. Then I will multiply this by 0.009, okay, divided by 10. So 9090 psi. In fact, this is the stress which is induced in the material. And then so now what do we have? So we know from here this is our stress. Now, okay, so okay, we are done. The question said we should calculate the factor of safety. Okay. By the way, we can also rewrite this as 1, 2, 3. So 9.09 k psi or ksi. Therefore, our factor of safety is how safe we are from our design. So, in other words, how are we safe, or how safe are we? It is given by the ultimate tensile strength divided by our stress which we have allowed. Okay, so it's going to be 16 ksi divided by 9.09. So what is it? 16 divided by 9.09. So that is 1.76. All right. And this is dimensionless. Okay. So in fact, this is the factor of safety. And all the time, the factor of safety must be greater than 1. Okay. So this problem has been solved. So we now have the factor of safety. Okay. Thank you very much for watching. I think we have solved all the problems here. Okay.